All right, so if you take out yesterday's graph, I'm just going to model the graph for you. I know that I kind of told you or showed you how to set it up yesterday. Um, Mine isn't going to be awesome, okay? But I'm just going to use it so that you can see kind of how the half-life, just as a quick refresher. So, for the record, we had strontium 90, which was the parent, and yttrium 90, which was the daughter. And the half-life was 28 years. And so when we finished, what year was it? 2164. Okay. Now, on your graph, you started with 2024. And by the end of it, which is probably right about here, you should have been at 2164. And then if you started here at 0 and went 5, you probably got to 35 up here. Okay. Now, the parent, remember, that one's unstable. But because of the law of conservation of mass, the parent doesn't just decay into nothingness. The parent turns into a daughter, and that one is yttrium 90, and that is stable. So when you did your graph yesterday, if you kind of did a smooth curve here, it should have looked like that ish. Okay. Now keep in mind, the parent is decaying. We don't know if it's losing alpha, beta, or gamma particles, but if it is an alpha particle, it is losing like a helium nucleus. So it's losing protons and neutrons. If it is a beta particle, it's just losing electrons. Okay. So the daughter starts at 0 and is going to kind of increase. So when we look at something that has a half-life, it's decreasing, like the parent is decreasing over time, and the daughter is increasing over time. Yes. No. You didn't have to do this. Like, you didn't have to do the daughter on your graph. I'm just showing you so that you understand that the total amount is still 32 grams. It's not disappearing. Okay. All right. Now, you could have used your actual graph if you set it up to answer these questions. I didn't. What I did was I just used the math because I figure that's what most of you probably did anyway. So if I'm looking at SR 90, that's the parent. And it says, how many would you have 16 years from now? So you could have gone to your graph and looked that up. Or you could have said to yourself, okay, SR 90 takes 28 years to decay in half. So after 28 years, I'd have 16 grams. But the problem is I didn't go 28 years. I only went 16 years. So for me, I did a little just kind of figuring here. I did half of 28 is 14. So after 14 years, I would have 8 grams. And if I decayed for 16 years, I might have 10 grams-ish. Okay? Now, how many will be left in 2050? Well, we know that the first year was 2052, right? So if I look for 2050, it's going to be probably a little bit less than 2052. So I don't know, it could be 14 grams. Again, this is just an estimation. You could have used your graph and gotten something similar. Now, how many grams are going to be left 100 years from now? Well, if you look, this was 2024. 100 years from now would be about right here, which would be 2124. And how many half-lives would have passed? This is 2052. So that's one half-life. This would be another half-life of like 78? Or 2080. What was it? 2080. This would be another half-life of 28. This would be another half-life of another 28, which would be around 100 years. So how much would I have left? I think it's safe to say somewhere between 4 and 2 grams-ish. Okay. Now, SR22 has a 28-year. Now listen, all I'm trying to get you to do here is to just use some critical thinking skills, some just prediction skills. So SR90, would it be useful for figuring out how old a dinosaur fossil is? Why not, Ian? Yeah, it's too short. I mean, what does geologic time say about how long ago the dinosaurs lived? A long time ago, right? Thousands, maybe millions of years ago. If that's true, then 28 years is not going to be enough time to get back there. So you'd need something like carbon-14, which has a 5,720 year half-life. Why? It's just more time. Okay. And then theoretically, again, you're just making a prediction, you're just making an estimation. Would your 32-gram sample ever be 0 grams? No, it wouldn't. Why? Yeah, it would just get infinitely smaller. You just keep dividing and dividing. It would just get infinitely smaller. Okay, again, all I'm looking for you to be able to do is just kind of think around what a half-life is, because really, that half-life is spontaneous anyway. It's not like clockwork and happens every 28 years. I mean, it's theoretical. Okay, so I'm going to give you about a minute, maybe 2, to find this lab. It is the Pennyium Lab. You picked it up earlier this week. Okay, so if you don't have this, I do have extras in that gray tote back there. Let's talk a little bit about what you're going to do today. So today, you are going to simulate a half-life using 100 pennies. Now, we've already reviewed what half-life is. It is the amount of time it takes in order for half of the substance to decay. So we could talk a little bit about the types of decay. Remember, if it is beta decay, it's getting rid of an electron. If it gets rid of an electron, that means I get a different element. Okay. If it is my protons, so if it is an alpha particle, if it's giving away those protons and neutrons like a helium nucleus, what it's doing, the neutrons are going to change and I create an isotope. So isotopes have different numbers of neutrons. If I change protons, what I change is the element itself. So when you did that uranium decay or the thorium decay, what you should notice is sometimes the mass changes, but you stay with the same element. Sometimes if the electrons or protons are changing, then what you're doing is you're actually changing the element itself, okay? So today, you're going to deal with radioactive pennies. If it is tails up, it is radioactive. If it is heads up, that means it is stable. So why do atoms go through radioactivity? Because they want to be stable. They are emitting particles so that they can become stable. And the half-life is the amount of time it takes to decay that substance in half. Please keep in mind that it is theoretical. So today, the side of the penny that's going to represent the stable, non-reactive atom is going to be the head side. So the tails are unstable, the heads are stable. Okay. Now, I do have enough stuff for you to work in groups of 2 today, and I don't care who you work with. And I also have enough stuff for if you don't want to work with anyone, you can work by yourself. I can't have you work in a group of 3 because there's not enough for 3 brains to do stuff today, okay? There's enough for 2, there's enough for 1, but 3 would just be way too many working on this activity. So I want you to see a couple things over in the lab setting, and I'm going to explain those now.